Hello everyone. In this video, I would like to work through a detailed example of Dijkstra's algorithm in lesson L13-1. Here's our pseudocode here for Dijkstra's algorithm, which we have already covered the pseudocode of and the implementation of in Python. So let's take a look at the following example graph, which I have adapted from Miller and Raynham's section on Dijkstra's algorithm. So we have 6 vertices in this graph, u, v, w, x, y, and z. The associated edge weights are listed, for example, u to v edge weight 2, x to y edge weight 1. So we're going to walk through Dijkstra's algorithm step by step with u as the starting vertex in order to find out what is the shortest path from u to each vertex in this graph. So in our Dijkstra's algorithm, we initialize all vertices distances to infinity, or any number that is too big to be realistic. We also set each vertice's predecessor to be 0 or none, something to note that there is no predecessor for this vertex yet. And we're going to set our origin vertex distance to 0. So here, initially, step number 1, I have all of our predecessors listed for u through z. So they're all listed to be 0, meaning they don't have any predecessors yet. The unvisited queue has every vertex in the graph listed with u at the front because u is our starting vertex and its distance is 0. So the lower the distance, the higher priority. So the lower distances will be at the front of our queue. And all the rest of the vertices are listed here in some arbitrary order, and their distance is set to infinity, INF, by default. So this is our initial setup for Dijkstra's algorithm for this graph here. Now, like I said before, u is our starting vertex, so by default we set u's distance to 0, which means in our first step, our first iteration through our while loop, while our unvisited queue is not empty, here is our unvisited queue. It is definitely not empty. We're going to dequeue from unvisited queue into curvy. So we're going to first dequeue u from our unvisited queue. And now we're going to walk through our code that is going to update, but to possibly update each adjacent vertex of u's predecessor and distance attributes. So here's u here in our graph. And now we're going to go through each adjacent vertex of u. So our adjacent vertices of u include v, w, and x. So, for example, processing our adjacent vertex v, so we see that v's predecessor is 0. We're now going to set it to u. V's predecessor is now u. And we're going to update the distance from v to u from infinity to 2, because 2 is smaller than infinity. So now we're going to decrease key v from infinity to 2. So here we see in our unvisited queue, v has now changed from v infinity to v2. Let's do the same thing for w. We're going to set w's predecessor to u and set the distance from w to u to be 5. Next, let's process x. So x's predecessor becomes u, and x's distance becomes 1. So here's our unvisited queue after we process all of the adjacent vertices of curvy u. And you can see in this graph here, the dark gray vertex is the current vertex, and these dashes represent the current shortest path back to our starting vertex, u. So next step, dequeue again from our unvisited queue. Well, at the front is x1. So now we're going to be processing x. So let's process each adjacent vertex of x. That includes y, w, v, and u. So the shortest distance from x to u is still x. So still the edge from x to u, which means predecessor for x is still u. We've already processed u. V, let's see if there's a shorter path from v through curve x, and there is not. The shortest path is still straight to u. So v's predecessor remains as u. Priority stays the same at 2. Now let's take a look at w. We see that actually with w, if we go through curve e, which is x, to u, we actually have a path distance of 4, which is less than 5. So now we're going to update w's predecessor to be x instead of u, and we're going to decrease key in order to update the priority. So w's priority went from 5 to 4. And now we're going to process y. So previously we had not discovered y yet, so now we have. We set y's predecessor to be x. That's how we currently know is the shortest path to get to u, and we're going to set its path distance to be 2. Through curve x to u is 1 plus the path distance from x to u, which is 1. 1 plus 1 is 2. So here's what our unvisited queue looks like. Note that v and y have the current same priority. So let's dequeue v at 2. So here's v here. Let's take a look at if there's any new shortest paths. So v to u shortest is still going to be the direct link to. So v's predecessor is u. If we go from w through v, we have a path distance of 5, which is not shorter than 4. So w's predecessor remains to be x. X's predecessor remains to be u, the direct link, which is the closest. And there are no other links out of v. We process w, we process x, and we've already processed u. So here's our unvisited queue. Next, we're going to dequeue y with priority 2. So here's y here. Now, let's take a look at v. V is not connected to y, so definitely no updating for v. W, if we go through curve e, which is y, to get to u, that would be 1 plus the distance y is from u, which is 2. So 1 plus 2 is 3, which is shorter than our previous distance of 4. So we're going to update w's predecessor to be y. And from y, we have now finally discovered z. So we're going to set z's predecessor to be y. And the distance from z to u through y is 1 plus the distance from y to u through x, which is 2. So 1 plus 2 is 3. Next, we're going to dequeue w3. Note that these have the same priority. So here we are dequeuing w with distance 3. And we don't have any shorter paths through w, so w's predecessor is going to remain to be y. And next we're going to dequeue z. And we don't have any updates here either. There's not a shorter path through w. So we are going to continue going through y, x, and u. And now our unvisited queue is empty, and we have figured out the shortest path from u to every other vertex in this graph. So for example, the shortest distance from u to z will follow z's predecessor links back to u. So z to y, y to x, and x to u for a total path distance of 3.